3.3 Normal distributions. One particularly important class of density curves has already appeared in figures 3.1 and 3.2, pages 74 and 75. These are called normal curves. The distributions they describe are called normal distributions. Normal distributions play a large role in statistics, but they are rather special and not at all normal in the sense of being usual or average. We capitalize normal to remind you that these curves are special. Look at the two normal curves in Figure 3.8. They illustrate several important facts. Figure 3.8. Two normal curves showing the mean mu and standard deviation, sigma. All normal curves have the same overall shape, symmetric, single-peaked, bell-shaped. Any specific normal curve is completely described by giving its mean, mu, and its standard deviation, sigma. The mean is located at the center of the symmetric curve and is the same as the median. Changing mu without changing sigma moves the normal curve along the horizontal axis without changing its variability. The standard deviation, sigma, controls the variability of a normal curve. When the standard deviation is larger, the area under the normal curve is less concentrated about the mean. The standard deviation, sigma, is the natural measure of variability for normal distributions. Not only do mu and sigma completely determine the shape of a normal curve, but we can also locate sigma by eye on a normal curve. Here's how. Imagine that you are skiing down a mountain that has the shape of a normal curve. At first, you descend at an ever steeper angle as you go out from the peak. Fortunately, before you find yourself going straight down, the slope begins to grow flatter rather than steeper as you go out and down. The points at which this change of curvature takes place are located at distance sigma on either side of the mean mu. You can feel the change as you run a pencil along a normal curve, and by doing that find, roughly, the standard deviation. Remember that mu and sigma alone do not specify the shape of most distributions, and that the shape of density curves in general does not reveal sigma. These are special properties of normal distributions. Normal distributions. A normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers, its mean mu and standard deviation sigma. The mean of a normal distribution is at the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side. Why are the normal distributions important in statistics? Here are three reasons. First, normal distributions are good descriptions for some distributions of real data. Distributions that are often close to normal include scores on tests taken by many people, such as Iowa test and SAT exams, repeated careful measurements of the same quantity, and characteristics of biological populations, such as lengths of crickets and yields of corn. Second, normal distributions are good approximations to the results of many kinds of chance outcomes, such as the proportion of heads in many tosses of a coin. Third, we will see that many statistical inference procedures based on normal distributions work well for other roughly symmetric distributions. However, many sets of data do not follow a normal distribution. Most income distributions, for example, are skewed to the right and so are not normal. Non-normal data, like non-normal people, not only are common, but also are sometimes more interesting than their normal counterparts. 3.4. The 68, 95, 99.7 rule. Although there are many normal curves, they all have common properties. In particular, all normal distributions obey the following rule, the 68, 95, 99.7 rule. In the normal distribution with mean mu and standard deviation sigma, approximately 68% of the observations fall within sigma of the mean mu. Approximately 95% of the observations fall within 2 standard deviations, 2 sigma of mu. Approximately 99.7% of the observations fall within 3 standard deviations, 3 sigma of mu. Figure 3.9 illustrates the 68, 95, 99.7 rule. By remembering these three numbers, you can think about normal distributions without constantly making detailed calculations. The 68, 95, 99.7 rule is sometimes called the empirical rule. Figure 3.9, the 68, 95, 99.7 rule for normal distributions. Example 3.2, Iowa test scores. Figures 3.1 and 3.2, see pages 74 and 75, show that the distribution of Iowa test vocabulary scores for 7th grade students in Gary, Indiana is close to normal. Suppose that the distribution is exactly normal with mean mu equals 6.84 and standard deviation sigma equals 1.55. These are the mean and standard deviation of the 947 actual scores. Figure 3.10 applies the 68, 95, 99.7 rule to the Iowa test scores. The 95 part of the rule says that approximately 95% of all scores are between mu minus 2 sigma equals 6.84 minus 2 times 1.55 equals 6.84 minus 3.1 equals 3.74, and mu plus 2 sigma equals 6.84 plus 2 times 1.55 equals 6.84 plus 3.10 equals 9.44. The other 5% of scores are outside this range. Because normal distributions are symmetric, half of these scores are lower than 3.74 and half are higher than 9.94. That is, about 2.5% of the scores are below 3.74 and 2.5% are above 9.94. Figure 3.10. The 68, 95, 99.7 rule applied to the distribution of Iowa test scores for 7th grade students in Gary, Indiana, for example 3.2. The mean and standard deviation are mu equals 6.84 and sigma equals 1.55. Okay, so you can see from the diagram on the x-axis you have the Iowa test score, there is no y-axis. Okay, so when you go one standard deviation out, you can see that that's 68% of the data. When you go 2 standard deviations out, you can see it's 95% of the data. And when you go 3 standard deviations out, you can see it's 99.7% of the data. And so each standard deviation is 1.55 here. And when you look at the 2 tails of the data, or the upper and the lower limits, after 2 sigma, it's the 5% left on either side, so that means there's 2.5% left on either side. The 68, 95, 99.7 rule describes distributions that are exactly normal. Real data, such as the actual Gary scores, are never exactly normal. For one thing, Iowa test scores are reported only to the nearest tenth. A score can be 9.9 or 10.0, but not 9.94. We use a normal distribution because it's a good approximation and because we think the knowledge that the test measures is continuous rather than stopping at tenths. How well does our work in example 3.2 describe the actual Iowa test scores? Well, 900 of the 947 scores are between 3.74 and 9.94. That's 95.04%, very accurate indeed. Of the remaining 47 scores, 20 are below 3.74 and 27 are above 9.94. The tails of the actual data are not quite equal as they would be in an exactly normal distribution. Normal distributions often describe real data better in the center of the distribution than in the extreme high and low tails. Example 3.3, Iowa test scores. Look again at figure 3.10. A score of 5.29 is 1 standard deviation below the mean. What percentage of scores are higher than 5.29? Find the answer by adding areas in the figure. Here is the calculation in pictures. The percentage between 5.29, which is negative 1 theta, and 8.39, which is 1 theta, is 68%. And then you add to that the percentage above 1 theta, 8.39, which is 16%, and then you get 68% plus 16% equals 84% is the percentage above 5.29, which is negative 1 theta. So approximately 84% of scores are higher than 5.29, negative 1 theta. Be sure you understand where the 16% came from. We know that 68% of scores are between 5.29, negative 1 theta, and 8.39, positive 1 theta. So 32% of scores are outside that range. These are equally split between the two tails, with 16% below negative 1 theta, 5.29, and 16% above positive 1 theta, 8.39. So you basically take the 32 and you divide it by 2 to get the 16%, then add it to the 68%, and that's your area, which shows the percentage of scores higher than 5.29, negative 1 theta. Because we will mention normal distributions often, a short notation is helpful. We abbreviate the normal distribution with mean mu and standard deviation sigma as n bracket mu, comma, sigma bracket. For example, the distribution of Gary Iowa test scores is approximately n bracket 6.84, comma 1.55 n bracket. Apply your knowledge. Upper arm lengths. Anthropomorphic data are measurements on the human body that can track growth and weight of infants and children and evaluate changes in the body that occur over the adult lifespan. The resulting data can be used in areas as diverse as ergonomics and clothing design. The upper arm length of males over 20 years old in the United States is approximately normal, with mean 39.1 centimeters and standard deviation 5.0 centimeters. Draw a normal curve on which this mean and standard deviation are correctly located. Hint: draw an unlabeled normal curve. Locate the points where the curvature changes, then add number labels on the horizontal axis. Figure 3.11 shows how arm length is measured. Figure 3.11. Correct tape placement when measuring upper arm length for exercise 3.5. The upper arm length is measured from the acromion process, the highest point of the shoulder, down the posterior surface of the arm to the tip of the olecranon process, the bony part of the mid-elbow. Upper arm lengths. The upper arm length of males over 20 years old in the United States is approximately normal, with mean 39.1 centimeters and standard deviation 5 centimeters. Use the 68, 95, 99.7 rule to answer the following questions. What range of lengths covers the middle 99.7% of this distribution? What percentage of men over 20 have upper arm lengths greater than 44.1 centimeters? 24.1 to 54.1 centimeters covers the middle 99.7% of the distribution, seen by using the graph, because it's basically the values from negative 3 sigma to 3 sigma, which covers 99.7% of the data. Those are the values at negative 3 sigma and positive 3 sigma. 16% of men have upper arm lengths greater than 44.1 centimeters. So you basically do some math by looking at the diagram. You see that 44.1 centimeters is mu plus 1 sigma. So basically 50% of the data lies below mu, and then between mu and 1 sigma is 34% of the data. So 50% plus 34% is 84% of the data lies below mu plus 1 sigma. And you want to find what lies above mu plus 1 sigma, which is 44.1. So you take 100 minus the 84%, and you get 16% left. Monsoon rains. The summer monsoon rains bring 80% of India's rainfall and are essential for the country's agriculture. Records going back more than a century show that the amount of monsoon rainfall varies from year to year according to a distribution that is approximately normal, with mean 852 millimeters and standard deviation 82 millimeters. Use the 68, 95, 99.7 rule to answer the following questions. Between what values do the monsoon rains fall in the middle 95% of all years? How small are the monsoon rains in the driest 2.5% of all years? The monsoon rain falls between 688 millimeters to 1,016 millimeters in the middle 95% of all years. So you basically find the range from mu minus 2 theta to mu plus 2 theta, which turns out to be mu minus 2 sigma is 688 and mu plus 2 sigma is 1016, so that's the range. 688 millimeters to 1016 millimeters is the middle 95%, because 95% corresponds to mu minus 2 sigma to mu plus 2 sigma, that range. In the driest 2.5% of all years, the monsoon rains are less than 688 millimeters. So basically what you do is, when you've taken out 95% of the data within mu minus 2 sigma to mu plus 2 sigma, you have 2 tails left, and each tail, the probability that remains is 2.5, because the tails add to 5% because the other part is 95%, so then you have 100%. So the left tail is 2.5%. So when you look at mu minus 2 sigma, that indicates where the tail is, and that's at 688 millimeters. So the dry season has less than 688 millimeters of rainfall per monsoon season.